All right, guys, let's get started. Today is Monday, October 19th. It's an A day. It's a great day to have AP Chemistry, or at least I hope so, and I think so. Today we're going to do a warm up and an exit ticket. The only assignment that we have that is out right now is the Chapter 12 NIMSY notes, and those details are in the Canvas assignment on Canvas. All right. So today we're going to try to wrap up Chapter 6. So we're going to finish Chapter 6 on thermochemistry. This is half of the thermo unit. Chapter 6 is on thermochemistry, which deals with energy relationships, how much heat is required to raise the temperature of a substance, like a cup of water, how much energy is required to raise the temperature of water from a certain temperature to another certain temperature. And then we got into Hess's law and heats of solution, how much heat is used or how much heat is required to uh, when something dissolves, how much heat is absorbed or released. So that's called the heat of solution. Today we'll look at heat of vaporization, heat of fusion, and do some practice calculations with that. We'll start chapter 12 kinetics, just a little bit on kinetics. On Wednesday, we'll do more kinetics. We'll do a precipitate slab. It's where I'm going to show a video, and you guys will kind of watch the video and then complete the lab. And hopefully that'll be kind of fun. And then I won't see you guys Friday because it'll be a B day. Okay, so review of Hess's law. The kind of guiding question here is that we want to know how we can determine the enthalpy for a reaction. And it's kind of like a puzzle, and I think it's really fun. These can get quite difficult, but usually there's not that many steps. Although I do remember seeing some that were pretty crazy. Um, but so far, looking through my notes and looking through my stuff, I haven't seen any that are super tricky. You may need to flip a reaction or multiply it by 2 or something like that. They're not too difficult, but sometimes when they're a little bit more difficult, it may be hard to put all the dots together and get the target reaction. It may be difficult to see because there's so much going on. But I do remember dealing with some that were pretty crazy. And if I see them, then we'll do those for practice. We're going to review heat calculations for phase changes. The guiding question for this is how can we calculate the heat needed to boil or melt water? So if we have water at 100 degrees Celsius and we want to boil it, how much heat's required? Or if we have solid ice and it's at 0 degrees Celsius and we want it to melt, how much energy do we need to put into it for it to melt? And then when we do kinetics, we're just going to do an introduction, and we're going to look at what factors affect the rate of a reaction. And then there's a lot of other little things that we'll look at today, but this is kind of the main thing. The other main thing that we're going to deal with today is the heating curve of water. We're going to make a graph that shows the heat changes when raising the temperature of water, boiling, freezing, all that kind of stuff. So we understand the relationships and what is the energy doing when these things are happening. And that's what thermochemistry is all about. Okay. So chapter 6, thermochemistry. All right, Hess's law. So we're going to start here. I felt like this is a good part to start from for today. Hess's law says that the change in enthalpy is the same whether the reaction occurs in one step or in several steps. That means that the enthalpy is not dependent on the reaction pathway. Okay, there are two things that we can do for enthalpy. We can reverse a reaction, and then the sign of its corresponding delta H is reversed, meaning that we multiply by -1. We flip the sign of it. And we'll be doing some more flipping of the sign with some other things too here. Some new stuff that we didn't do last time. And then if the coefficients in the balanced reaction are multiplied by some integer, then the value of our delta H is also multiplied by that integer. So that's the two things we can do here with Hess's law. And then the sum of the delta H's for each step equals the delta H for the total reaction. So we're going to have a couple of reactions here. And we're going to flip them and multiply them by some number. And then when we add up each step in our reaction, some things should cancel out, and the only thing that remains should be our target reaction. And if you've got the reaction and they add up just right, then the delta H's will add up just right if you do the same thing with their numbers. If the reaction is reversed, then the sign of delta H is reversed. If you multiply by some coefficient, some number, 2 or 3, then the delta H for that reaction will also be multiplied by the integer, and then you add up all of the delta H's to get the total delta H for the reaction. So let's look at the example that we did last time. This was a pretty simple one. We've got 3 reactions here, and we are going to try to get this target reaction. This is our target reaction. Okay, there we go. And we've got these 3 reactions here. All right, so if we look at our reaction, the first thing we have in there is 2 carbons. So let's find the reaction that has carbon in it. That's the second reaction, this one here. And then we see that it has 1 carbon in it. We need 2 because there's 2 in our target reaction. So we're going to multiply that reaction by 2. So I'm going to rewrite that reaction. 2 times carbon plus 2 O2, and that will give us 2 CO2s. And the delta H for that will be 2. I'm just going to make a table of delta H's here. That's going to be 2 times negative 393.5, which will give us, where's my number? Minus 787. That'll give us minus 787 kilojoules per mole. And then if we look at our top reaction, well, let's keep going. So we have this one, right? That one's good. We found our 2 carbons. Now let's look at our hydrogen. This third reaction has hydrogen in it. Yes, it has oxygen and water in it, but since it has hydrogen, let's go ahead and say we're going to need that equation exactly as it is originally, and then hope that the oxygen and the water cancel out. And they will have to cancel out, but let's not worry about that right now. Let's just make sure that we get our hydrogen. Okay, and then the delta H for this reaction is negative 285.9 kilojoules. Okay, and so now we have our water, or I'm sorry, we have our hydrogen, our H2. Now we have C2H2. Ooh, C2H2. I'm trying to think what this thing is. It's only got 2 hydrogens. This is acetylene, and it looks like this. It's got a triple bond between those carbons. All right, and the reason for that is carbon has to have 4 bonded partners, and so since there's only 1 hydrogen for each of those carbons, it must be a triple bond in between, and we'll talk more about that when we get to bonding. I know I keep bringing up bonding because I like to draw the structure of the molecule and all that. I find it kind of fun. So that's our structure for our molecule, and that's acetylene, which is a hydrocarbon. We have our hydrocarbon in this equation, but it's shown as a reactant. We need it as a product, so let's flip this reaction. So I'm going to write flip, and then I'm going to change the sign of this. It's negative, so I'm going to do it positive. So now I'm going to rewrite this equation down here, flipped. We have 2 CO2 right here. We have our water right here. Those 2 will react to give us our C2H2 and 5/2 O2. And then our delta H for this will be a positive 1299.6. Okay, so now what we're going to do is add up these reactions, and they should get us our target reaction with nothing else left over. Nothing left, or nothing missing, and nothing left over. It needs to be exactly this reaction right here. And then we're going to add up our delta H's, and that should be our answer as long as everything in our reaction cancels out and we get the target reaction. So let's see what we get. Okay, we have our 2 carbons here, and that's not going to cancel anywhere. We have our 2 H's here, so H2. Okay, so 2C plus H2. We got this part here. 2O2 is the same thing as 4 How did I do this before? 202. That's 4 over 202. So if I have 4 over 202 right here, and I add the 1/2, what do I get? 4 plus 1 is 5, so I get 5 over 2. Okay, so I have 5 over 2 on the reactant side, 5/2 O2. And then look on my product side. I have 5 over 2, so that will cancel with all of the oxygen. So all of our oxygen cancels. All right, then look, we got water on this side. The water will cancel. We got 2 CO2s here. It will cancel here. And notice that we have everything removed except for our target reaction. So we've done everything we needed to do. C2H2. Okay, that's our target reaction. And then if we add up all of these guys, if we add up negative 787 plus the negative 285.9 and then a positive 1299.6, we will get our delta H of our reaction, which we will end up getting the total delta H for this target reaction will be 226.7 kilojoules per mole of reaction. So that's our answer for this one. So I just wanted to go through this one again since it's really simple and it's easy to kind of see what's going on. And so that is Hess's law. Okay, and then I've got, actually I should save that. Darn it. It's okay, I'm recording. So let's see. So here's the same thing, but kind of done on the PowerPoint for reference. If you guys come back to the PowerPoints later. I would always come back to the videos though, but if you don't have time to kind of click through and find what you need in the video, then the PowerPoints may be a little easier, a little faster to get what you need. Okay, let's do another one. That was number 1. Where's number 2? Number 2, we have a couple reactions. And let me see if I can actually get the reactions pulled up. There we go. So here's our 2 reactions. We have carbon plus O2 makes CO2, and we have its delta H. We have carbon monoxide plus 1/2 O2 to give us CO2, and we have its heat of reaction. We want to know the heat of combustion, which is a combustion reaction. So it's the enthalpy for this reaction, but we can call it the heat of combustion if it's a combustion reaction. All right. So if we have a combustion reaction, darn it, keep touching the iPad. So combustion reaction is where we have something, we add O2, right? And so we're going to add C plus some O2, and we're going to get carbon monoxide, right? We're starting with carbon, and we're making CO. So this is a combustion reaction where we make carbon monoxide. We add carbon with oxygen. That's combustion. And so we can call this heat of combustion, or enthalpy of combustion. We're just calculating the enthalpy. But I do kind of want to hit this because there are some terms here. And then when we do solution, if you see a problem that says, what is the heat of solution? That means what is the energy change associated with dissolving a solid or making a solution? That looks terrible. Let me move my iPad. Sometimes I just have issues with this. Salt. So if you want to dissolve the salt in water, then the heat associated with doing that is called the heat of solution. Okay, so let's go ahead and try this one. We want carbon as a reactant and carbon monoxide as a product. We're not told what else needs to be in the reaction. So let's look at our reactions. We have carbon here, and so we need this reaction as it is. So we'll need this reaction. But in the next reaction, we have CO2 as a reactant. We want it as a product, right? And so let's flip that reaction. So let's flip. And if you think about this mathematically, when you flip a reaction, you are multiplying it by -1 or dividing it by -1, but we're flipping it. And so we're going to flip this here. Multiply by -1 or flip the sign of this. And so it'll be a positive 283 kilojoules. So then let's write our two reactions together. The second one flipped, and then see if they add up to the reaction that we want. All we know right now is that carbon needs to be a reactant and carbon monoxide needs to be a product. And we're just given these two reactions. So we're going to work with what we have and produce a reaction that will give us that. So we have C plus O2 makes CO2, and then we have CO2 breaking down to form CO and 1/2 O2. Okay, so if we add these guys up, it looks like the carbon monoxide will cancel out here. And then on one side we have O2, which again is 2/2. And this is 1/2. And so 1/2 of that oxygen will cancel. So this will become 1/2 O2, and this one will be gone. And so what do we have left? Carbon plus 1/2 O2. Doesn't like it when I try to write the bottom. So carbon plus 1/2 O2 will make this guy, CO2. So just CO. So that's our reaction. Now we're going to take the negative 393.5 kilojoules from the first reaction, and we're going to add the 283 from the second reaction, and we'll get our net enthalpy for our target reaction, which will be negative 110.5 kilojoules per mole. Boom. Awesome. I like these. These are fun. These are kind of almost too easy, but it's good to start off easy, right? We wanna make sure we're getting it. Okay. Fun. So I think that's it for Hess's law. This is all the same one. Okay, let's talk about the standard enthalpy of formation. So this is a symbol for it. Delta means change in heat. Remember, we're looking at the heat associated with a reactant versus a product. So it's the products minus the reactants. How does the energy compare between them? That's enthalpy. What is the change in energy? So the change in enthalpy that accompanies the formation of 1 mole of a compound. So if I make a compound, let's say water, well, then it's going to be take H2 plus O2 and make water. Essentially, I know this isn't balanced, but essentially the delta H of water, so the delta H of formation for water will be associated with forming the compound water from its elements with all of these substances at standard states. And again, that's what the little degree symbol means, right? The little degree symbol there is tells us that it's at standard states. And there, like I said, there are some examples where they're not at standard state, and we'll have to do something different at that point. But for now, everything that we're doing is at standard states. That means that the pressure is 1 atm and the temperature is 298 Kelvin or 25 degrees Celsius. Remember, to get from the degrees Celsius to Kelvin, you add 273, essentially. So whatever the degree Celsius is, to get from that to Kelvin is plus 273. And this is a conversion that we need to know. We need to be able to do. From Celsius to Fahrenheit, not so much. We don't do anything in Fahrenheit in AP chemistry. And that's a good thing. Standard states. Okay, so if it's a gas, then the pressure is 1 atm, 1 atmosphere, which again is the weight of air above your head. For a substance in solution, the concentration is 1 molar, 1 mole per liter. That means 1 mole for every liter of solution. For a pure substance in condensed state, if it's a liquid or solid, then the standard state is the pure liquid or the pure solid. So if we had water and it was a liquid, then it would be in its state. So for a pure substance in a condensed state, the standard state is the pure. So it'd be a pure liquid. Okay. For an element, the standard state is the form in which the element exists at these conditions. So if it's an element and we're looking at the standard state, it's going to be the form that the element is at under those conditions. Some elements are solid or liquid at different temperatures. So most elements are metals, or I'm sorry, solids. Most metals, most elements are solid at room temperature. 25 degrees is pretty close to room temperature. There are some gases, right, at the top of the top of the periodic table. There's oxygen, nitrogen, fluorine, chlorine. What else? Oxygen. And then we got our noble gases, and then we've got some liquids on the periodic table as well. I just thought I'd do this real quick. This is kind of cool. There's two liquids on the periodic table. There's mercury, Hg, and bromine. So, and then one element that's a weird and it's a solid is iodine. Iodine is a solid, which is kind of cool. Although all the other halogens, or most of them, are gases. All right. Okay, so we can find the delta H values in an appendix, or in the problem they're going to give it to us. So we'll have the delta H's for many of the substances. Some of them we will not. We may not need them, or maybe we're going to be trying to determine the delta H for a given substance if we don't have it. If you also, we're not going to be given the delta H for elements, because the delta H for a pure element at standard state is defined as 0. Because the delta H of formation to make a compound, or to make a substance, is a given value. So like if we're going to make water, the delta H of formation is the energy needed to make water from elements, from pure elements. So if we have a pure element, there is no energy needed to make it, right? Because we're not making a compound, it's still an element, and so it's defined as 0. So if we had H2, if we had it as a gas, or O2, or I2, which is a solid, or Br2, which is a liquid, or fluorine gas. These are all pure elements, and the delta H for formation for each of these would be 0. Or if we had a solid metal like zinc or iron, then there's a pure element, and the delta H would be 0. Okay, so let's try this one. This is one that we did together, but I want to do it again. We have our reaction here. Here's our reaction. ClF3, so chlorine trifluoride is what we would call that. This is ammonia, nitrogen gas, hydrogen fluoride gas, and then pure chlorine as an element. The delta H for this total reaction is 1196, and we want to know what the delta H is for this compound, this chlorine trifluoride, and then we're given the delta H's for the other two compounds. So let me modify my PowerPoint so that I have room to do this. Let's copy paste. I need to get rid of this table. There we go. Let's try this. So we know that the delta H for the reaction will be equal to the sum of the delta H's at standard states for the products minus the sum of the delta H's of the reactants. Remember, it's always products minus reactants. And flipping these will get you in a lot of trouble. So we know that the total delta H is 1196, and I'm going to start with my product. So I'm going to start with these guys. So nitrogen is 0. We have 6HF, so that's 6 times the negative 271 from that table that I erased, and then plus the 0, which is the chlorine. So that's our products. We're going to take all of that And that's why I put it in brackets, and we're going to subtract the reactants. Here's our reactants, and we're doing this in a different color. Make it purdy. Here's our reactants. We have 2 times ClF3, and to me, I just like to write 2x. 2 times the delta H subformation for that molecule. If you wanted to, you could write delta H of formation for ClF3 instead of X, but I find this to be a little bit cleaner. And then we're going to add that to 2 times the delta H for ammonia, which is negative 46. Okay. When I do this side, so I still have 1196 here. That's my total. I know that all of this is going to add up to 1196. And so the zeros can just disappear. I'm going to do 6 times negative 271. That will give me negative 1626. And this is all kilojoules, so maybe I should write kilojoules somewhere. And then I'm going to take that, subtract what I get on this side. 2, so this part's just 2x. I'm going to leave that there, 2x. And then 46 times 2 is 92. So I'm going to do minus 92. Okay, now let's distribute that negative. So I got 1196 here is equal to a minus 1626 kilojoules. And then this minus 2x, which is what we're solving for. And then I got a minus, which is a positive. So I'm going to add 92. Okay, now we're going to do some combining like terms. I'm going to put all the numbers on the left side. So I'm going to add 1626 to this side to get rid of that. And then I'm going to subtract the 92 from both sides. Okay. And then I'm on this side, I'm going to have a minus 2x. So my answer is going to be negative at the end. And then all of this added up will give me the left side. And let's see, what do we get? We end up with minus, actually it's a positive. We're going to end up with 2730 kilojoules is equal to a minus 2x. Then we just divide both sides by minus 2. And when I divide by minus 2, it makes that a negative. So 2730 divided by negative 2 will tell me the delta H of formation for my chlorine trifluoride. And it's a negative 136 or 1365 kilojoules per mole. So every mole of this stuff will need 1365 kilojoules in order to make that compound from the elements, from chlorine and fluorine. Okay, so this is an example where we have our reaction. This is what we're doing in the lab. And we find the delta H's for just about everything else. But this guy was not studied in the lab for whatever reason. And so we don't know the delta H for that substance. So we can find it with this fun algebra problem, right? Okay. And I think that brings us to the end of our review. Now we'll do some new stuff. Okay. So I'm just going to do some clicking and some talking for a second, and then we'll do some more stuff. Okay. Calorimetry is a measure of heat flow. We use a calorimeter to do this. Heat capacity is the amount of heat needed to raise the temperature of an object by 1 degree Celsius. Now, heat capacity can be in many different units. It could be used in Kelvin. It could be used in Celsius, and we use both of them. So it's either the temperature needed to raise the 1 gram of an object 1 Kelvin temperature or 1 degree Celsius, either one. And then molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of substance by 1 Kelvin. Specific heat is the main one that I like to use, and this is specific heat capacity. This is the amount of heat needed to raise 1 gram of a substance by 1 Kelvin. Okay. Usually we're talking water. So just some definitions here. How do you get your molar heat capacity? You take your molar mass times your specific heat. Okay, so you can find the specific heat of the substance. If you multiply it by the molar mass, then you get the molar heat capacity. Okay. We calculate the heat of a substance loses or gains using these two equations. All right, so this one's familiar. We've talked about this one. The heat needed to raise the temperature of an object is equal to MCAT. M is the mass in grams. C is the specific heat capacity, which is the energy required to raise 1 gram by 1 degree Celsius. And then the change in temperature is the final minus the initial temperature. Okay. So this is the heat. This is mass in grams. This is the heat capacity, which heat capacity is usually joules per gram degree Celsius. And then change in temperature is the final temperature minus the initial temperature. Okay. Now this other heat one it says Q is equal to positive or negative. So it could be a positive or negative at the front, depending on what we need, times the mass, again in grams. And then this is going to be the molar heat of vaporization, molar heat of, maybe not molar. It's going to be the heat of fusion. So I like to write this equation as this: Q equals M times delta H. Okay, and so what can happen here is we will find a delta H that we need from a table or from the description of the problem. It could be the delta H of vaporization, the energy required to boil water, or it could be the delta H of fusion, the energy required to melt water. All right, so vaporization is boiling, and fusion is melting, which I know is hard to, it's tricky to remember. I have a hard time remembering that. So let's look at this real quick. Okay, let me just erase this here. So here's our equation at the top. Q equals M times delta H. We've got vaporization, so delta H of usually V or VAP is boiling. Now let's say that we wanted to do the opposite. Let's say that we wanted to condense water. The delta H of condensation is equal to the exact opposite of vaporization because of the opposite process. Vaporization is going from the liquid to the gas. Condensation is going from the gas to the liquid. Kind of what your soda does when it sits there for a while. And so that's a negative delta H of vaporization. And so if you look on a table or in the problem, they will usually tell you the delta H of the vaporization. They have to. So that's a value that we're going to be given. All right, but they don't usually tell you the heat of condensation or the enthalpy of condensation. Usually they call it the heat of, so heat of condensation. They're not going to tell you that, but it's the opposite of the heat of vaporization for that substance. And then we have our delta H for fusion, which is melting. Well, what if we wanted to freeze something? The delta H of freezing is equal to the negative delta H of fusion. All right, and so how do we find the heat required to change the phase of a substance? We're going to do this: mass times the change in H. And the unit for the change in H will be joule per gram. And that's why mass needs to be in grams. Again, this is one of those few equations in chemistry where we can use grams. And this one we use degrees Celsius, which is really weird. Okay, so what I want to do now is try to do some of these problems. Okay, so let's open up this. And let me kind of space them out a little bit more so I have enough room. And I'm going to assign this to you guys And basically, I'm going to do most of them or many of them, but I want you guys to finish them. Okay. And so I'll give you guys this as a Google Doc, and then I just want you guys to type your answers. But kind of show some work, show me what equation you used, and kind of how you got your answer. Or if you want to just do it all on paper and show your work handwritten, that's fine too. So let's try this one. Calculate the number of joules needed to turn 325 grams of water at 100 degrees Celsius to steam. So at this point, we have the same temperature, 100 degrees, 100 degrees. So we are not changing the temperature. We are just turning liquid water to steam. Liquid to gas. Okay, so we're going to do, and I almost need to make this bigger. Maybe if I zoom in a little bit. There we go. So Q equals M times delta H. And this is going to be vaporization. Now the delta H of vaporization, oh, what happened to my stuff? There we go. My delta H of my vaporization is equal to 2260 joules per gram. And then when we need the delta H of fusion, I'll write that down. So we're given this value. It's just in this problem for whatever reason. It's just not in the problem, but it would be a number that is given. So we're just going to multiply that by the mass. 325 times 2260. We get a large number. We get 226,000, and that's joules. If you wanted to divide it by 1,000 and get it in kilojoules, it'd be 226 kilojoules. Okay. All right, number 2, calculate the heat released when 875 grams of water at 0 degrees Celsius turns to ice at 0. So notice that the temperature is not changing. So this is a phase change. Q is equal to M times delta H. The delta H of fusion, I'm going to write up here, or melting, is equal to 333.55, and it's positive. It's positive because we have to put energy in order for it to melt. So we're going to do 875 grams times 333.55. And so that is 291,856 joules. Or if you wanted to round it, you could maybe round it to 292 kilojoules. I just want to put it in kilojoules, but it's both. Either one of these is a good answer. And usually we'll get joules. It's just it might be sometimes if the number gets large enough, it might be better to put it in kilojoules because some of these numbers that we're going to get beyond a million joules. So there's a lot of numbers. Let me do let me get a whiteboard and clear what we got. I want to draw the heating curve for water before we continue. So here is a graph. On this side, we have degrees Celsius. The bottom is going to be maybe negative 40 degrees Celsius. The top is going to be 100. Oh, I keep hitting this little button. There we go. The top is going to be 140 degrees Celsius. Then this is going to be heat absorbed. And it's not going to be like, I'm not going to put little tick marks. It's just as you go to the right, you get more heat absorbed. So let's start with a solid. Let's start with solid ice. So here we are down here. And we're basically going to take some solid ice. Let's put it on the table. Let's heat up the room. Let's heat it up. What's going to happen is we're going to have a straight line increase until we get to 0 degrees Celsius. And so if we had solid ice and we want to get it to melt, we heat the temperature from negative 40 until it gets down to 0. We want to warm it up. Warm up that ice until it melts. And then when it starts to melt, it will flatline. And actually, that's a little too long. Let's make it a little shorter. So it'll flatline, and that's called latent heat, meaning that is heat that goes into the bonds Latent heat is heat that is used to break the bonds. We're taking the bonds, that hydrogen bonds in a solid, and we're kind of breaking them a little bit so that they're it's going to be liquid. And so we'll still have interactions between the liquid. We're still going to have hydrogen bonds between the water molecules. It's just going to be less so. Did I spell latent right? Latent heat. There we go. It just looked weird. And then once we have melted that solid and continue beyond 0 degrees Celsius, so now we're heating above 0 degrees Celsius. So now we're going to heat our water again. And then what happens right here at 100 degrees Celsius? Boiling. And so now we're going to boil. And this is going to be there, and then a gas. All right, so let's label our heating curve. So down here, we have a solid between -40 or negative temperature in degrees Celsius up to 0 as a solid. This is a liquid. And then up here is a gas. This part right here is a gas. And then let's label our processes. What is this right here? This is melting. And so we're going to do Q equals M delta H of fusion. Okay, I know that looks bad. It's hard because I'm zoomed in a whole lot on the iPad. And then this is boiling here. So this is going to be Q equals M times the delta H of vaporization. Okay. What equation are we going to use between here and here? We're going to be heating the temperature from -40 or so up to 0. So that's a change in temperature. So we're going to use Q equals MCAT. Okay, so on the sloped lines where we got a liquid or a solid or a gas, these three parts, we're going to use Q equals MCAT. Because we're raising the temperature of the substance. We're not doing a phase change. And then same thing right here. That's Q equals MCAT. Okay. If we're going this way, we can say that energy is absorbed. Okay. So that's endothermic. And I know that might sound opposite of what you're thinking. But if we go from ice to liquid, you have to put energy in to melt it. If you have liquid water and you want gas, you got to put energy in. So going up that way is endothermic, and then going back this way is exothermic. And so if we have an exothermic reaction, if we're going to condense water vapor, we're going to do Q equals M times the negative delta H of vaporization, because we're doing the opposite of vaporization. And then same thing over here with fusion. If we want to freeze the substance instead of melt it, instead of fusion, then we're going to do the negative of the fusion because we're doing the opposite. So there's a lot of cool relationships here. All right, that was fun. All right, now I'm trying to remember which one we did. We did the first two, right? Maybe just to the first one. Okay. Number 2, calculate the heat released when 875 grams of water at 0 turns to ice. Maybe we did that one. We did that one. Yeah. Okay. Let's do number 3. Calculate the number of joules needed to vaporize 2 times 10 to the 2 or 200 grams of liquid ammonia, NH3, at its boiling point and produce ammonia vapor at the same temperature. So if we read this carefully, we are not changing the temperature. And so we're doing Q equals M times delta H, vaporization. All right. And so Q equals the mass, which is 200 grams times 1374 joules per gram. So notice in this question, they tell us that the heat of vaporization for ammonia is this. And so we multiply these out, grams cancels, and we get 274,800 joules. Okay. Or 275 kilojoules if we wanted to round a lot. Okay. These are pretty easy. Number 6. So now I'm going to switch to number 6 because these are almost the same. And I like these questions, and I like to assign them because you've got the delta H of formation. So the delta H of formation for iodine is right here. The delta H for melting palladium is right there. Okay, so number 6, calculate the heat released when 454 grams of steam at 100 degrees condenses and then cools to water at 30 degrees. So let's think about what is happening. We need to condense the water. So we have water at temperature. So initial temperature, keep hitting that button. Initial temperature is at 100 degrees Celsius. The first thing we're going to do is take that water at 100 degrees Celsius, or that steam at 100 degrees Celsius, and we're going to condense it. So the first thing we're going to do is condense it. And then cool it from 100 degrees Celsius to 30 degrees Celsius. We're going to cool it down. Okay. So the Q1 will be condensing, which will be equal to M times the delta H of condensing, which isn't really a thing. So it's truly going to be, or actually going to be, delta H of M times the negative delta H of vaporization, which will be equal to 454 times negative 2260, which is the heat of vaporization for water. And so that's going to be 1,026,040 joules. All right, Q2 is raising the temperature from 100 down to 30. So that's going to be MC delta T, which is going to be 454 grams times 4.18, which is the heat capacity of water. And I would memorize that. That's pretty common, and they may not give you that. If you look on the AP Chemistry formula chart that I shared with you guys either last week or the week before, it may be in there, but I'm not sure. But 4.18 is just a very common number. And then we're going to do 30 minus 100. Remember, it's the final temperature minus the initial temperature. And so we multiply that out, and we get negative 132,840. And so to get our total heat, we add these up, which I'm looking at my notes, and I don't remember seeing me doing that. Did I not add them up? Okay, well, we would add these two up. This is the energy needed to condense it, which is positive. Wait, is this negative? This is negative. And then the next one's definitely negative. And so we would add those two numbers. And that would be the total heat needed, or the total heat released when this happens. Now, why is it released? Because we're starting with steam and we're condensing it. So that's exothermic. It's energy released. So then our answer will be negative. It'll be 2 million and something. Okay, that's number 6. Let's do number 7. I think that's our last one for this stuff. Calculate the heat change needed to change 475 grams of water at 40 degrees Celsius to steam at 100 degrees Celsius. So first we're going to need to take the water, liquid water at 40 degrees and increase it to 100, and then we're going to need to boil it. Okay, so Q1 will be MCAT, which will be 475 times 4.18. I think there's a 4 after that. I don't remember. 4.18 is what I remember. And then the change in temperature, final minus initial. So 100 minus 40. When we do that, we get 119,130 joules. So that's the energy required to increase the temperature from 40 to 100. And then Q2 is we're going to go ahead and vaporize it. Going to boil it. So that's going to be 475 times 2260, which is the heat of vaporization for water. And we're going to get 1,075,000. Wait, 73,500. All right, and then I do Q1 plus Q2, and I get 1,192,630 joules. And so that would be the total heat needed to take 475 grams of water at 40 degrees. That would be liquid water. Water is liquid between 0 degrees Celsius and 100. Water is gas above 100, and then water is freezing equal to or less than 0. Okay, that's a really nice thing about the Celsius scale is 0 degrees Celsius to 100 degrees Celsius. So 0 is freezing, and then 100 is boiling. And then just for fun, let's put the Fahrenheit. 32 degrees Fahrenheit is freezing. 212 is boiling for Fahrenheit. Okay, so that's it for heating curve stuff. This was great. I hope you guys learned a lot. Let's look at our PowerPoints and finish our PowerPoints. And I'm going to try to do this quickly because I know I've been talking a long time. So we did this stuff. Q is the heat. M is the mass. We have heat capacity in here. Delta T is the change in temperature. And then we had Cx, which is just the delta H of the substance. So don't let this confuse you. Cx is either equal to delta H of vaporization or delta H of fusion. Okay, so you're just going to multiply the mass by that delta H. That's all we're doing. Okay, so here's our heating curve. Solid up until here, and then it's turning into a liquid, and then it's a liquid here, then it's turning into a gas, and then it's a gas there. Heat added, endothermic, heat removed, heat released, exothermic. Okay, and here's an example. I'm not going to go over the example here, but it's asking what is the enthalpy change when 679 grams of water at this temperature are converted into water vapor at this temperature. And then this is the steps for how we would do it. We look at the graph, we see where we're at, and we see where we need to be, and we look at that. So first we're going to heat the liquid. We're going to use MCAT for that, and then we are going to boil the liquid. So this is kind of similar to the example we just did. And then we add them up. Oh, then we're going to heat the gas, right? Because at 100, it'll turn into a gas. But if you want to get it to 121.2 degrees Celsius, you've got to heat it some more after. So this one is 3 steps. So that's our total delta H for that one. and it's positive because we're putting heat in. We're putting energy in to break the bonds. With the coffee cup calorimeter, a reaction is carried out under constant pressure. The pressure is constant because the calorimeter is not sealed if the pressure is not constant. And we want no heat exchange between the cup and the surroundings. If we had a heat exchange, then the solution might absorb heat from the surroundings. Okay, so the heat absorbed in the coffee cup calorimeter is equal to the negative of the heat released. For dilute aqueous solutions, so anything dissolved in water, the heat capacity is 4.18 joules per gram Kelvin. Or I think it's the same joules per degree Celsius. You know what, guys? This might be a different number if it's Celsius. I'll have to look into that. This is specific heat of water. Here's another example. When 50 milliliters of this acid and this acid are mixed, or silver nitrate and that's mixed, the temperature goes from this temperature to this temperature. Calculate the enthalpy change for the reaction per mole. We did one just like this. So we're going to assume that the mixture is just water, essentially. Yeah, I know it's stuff mixed in water, but most of it is water. It's dilute. It means it's mostly water. And then the mass is 100 grams. So you can assume 100 grams total. So we can do MCAT here. 100 grams times 4.18 times the change in temperature. There we go. That's the heat. So a couple assumptions here to do this one. And then, okay, that's the joules for 100 grams. Then we're going to divide that for the moles. We have 0.005 moles of silver nitrate. So there we go. And that's negative. All right, combustion reactions are studied using constant volume calorimetry. That means that the volume is constant. These are called bomb calorimeters. The heat capacity of the bomb calorimeter must be known. It's called the C-cal. And there's an example in here that you guys can look at. Again, we assume that no energy escapes into the surroundings, so that the heat absorbed by the bomb calorimeter is equal to the heat given off by the reaction. Here's a picture of one right here. And then here's an example. Multiply this is the molar mass here. This is the heat capacity. Okay. We talked about Hess's law, so I'm going to skip over Hess's law. But here's some more PowerPoints over Hess's law that might be helpful. Okay, so I'm just going to click through it because we've already talked about Hess's law quite a bit. So this gives you guys more examples to look through. And if anything in the examples don't make sense, just let me know. A couple examples here. This one looks fun. Okay. And I will certainly share this PowerPoint with you guys. All right, let's talk about kinetics real quick. I know you guys are nearing the end. Kinetics is all about speed. What influences the rate of a reaction? So here is a reaction for potassium nitrate, which is gunpowder. Gunpowder burns quickly, but the reaction is much slower than nitroglycerin detonating. Okay, so why is that? Oh, and there's nitroglycerin, which I think is TNT, dynamite, I think. Okay. Enzymes are huge molecules that speed up reactions in biological systems. So there's enzymes that we have in our body that catalyze and speed up reactions. All right, so what are the factors that affect the speed of a reaction? Generally, the concentration of reactions increases the rate. Okay, so if you increase the concentration of the reactants, they're going to turn into the products faster because you have more of them. And that means that more reactions will take place as time goes on, which means that the reaction will happen faster. So the more concentration you have, the faster the rate. How about temperature? Remember how I said heat them up, speed them up? When molecules are moving faster, because the temperature is higher, these molecules will run into each other more so. And every time they run into each other, they have a potential to make the products, right? Because that's how they're going to react anyway, is gas molecules colliding in midair. And so as the temperature goes up, the speed of the molecules goes up, the kinetic energy is increased, and so the rate of the reaction will increase. Very cool. If you have a catalyst, if you add a catalyst, then you can get a reaction to happen. Okay, and I'll show you guys some reactions that are catalyzed that are pretty cool. There's the elephant's toothpaste. There's the genie in a bottle reaction, and these are catalyzed, meaning that you add some kind of substance to it, and it interacts with the reaction and the reactants just right to force the reaction to happen quickly. It speeds it up. And so the reaction rate goes up with the catalyst. Okay, the catalyst works to lower the activation energy. The catalyst is never written in the reaction like a reactant or a product. It's usually written over the arrow. And so let me see if I can think of an example. Let's just do a generic example. Let's just do A plus B makes C. And then if we had like a palladium catalyst, the symbol for palladium is PD. And so I would put PD over the arrow if I wanted to indicate that it had a catalyst. And a catalyst lowers the activation energy, which again is that hump. So if you had the reactants, you have the hump, and then they go down to make the products, that's the activation energy. It's the hump that the reactants have to get over in order for the reaction to happen. It is not consumed in the reaction. It just speeds it up. It changes the way that the reaction happens, the mechanism of the reaction. What's actually going on with the molecules. So here's our things. If you increase the surface area, then the rate goes up. Okay, so what does that mean? Let's think about a cube. Let's take a big cube of sugar. Okay, so this is sugar. Let's take this sugar and put it in a glass of water. Well, when the water attacks the sugar, it can attack this surface. Whoa, what's going on? There we go. It can attack this surface. It can attack this side. It can attack the top. But it can't really get to the center of the sugar cube. And so it can only dissolve it so fast. But let's take that sugar cube and break it up into a bunch of little cubes. Let's break it up into 100 tiny little sugar cubes or sugar grains, right? And so now the surface area on the sugar is increased exponentially because all of them have exposed surfaces, right? And so it will eat it faster. Okay. Okay, what else we got? Also, as mixing increases, the rate increases. So if you take sugar and dissolve it in water, we all know that if you stir it, it will mix it quicker. Okay, reaction rates are usually expressed as molar per second. So that is moles per liter divided by a second. And so that's concentration in moles per liter, molarity. I was looking for the word there, molarity over a second, and that's over time. So concentration per time. The rate of the reaction is the concentration, the change in the concentration over time. So change in the molarity over time in seconds. So change in X. And remember when we write concentration, so concentration of let's say if I wanted to say concentration of water, I would put brackets like that. And so it's the change in the concentration. Okay, so if I had hydrochloric acid, the change in the concentration of hydrochloric acid would look like this. Change and then brackets Brackets means concentration of, which means molarity, which is moles per liter. Okay. Let's see what this graph is. So this is concentration of substance versus time, and we'll finish off here. So as the reaction happens, this is a graph of the concentration and time. And let's look and see how they change. If it's a reactant, we will have a high concentration at the beginning of the reaction, and it will have this nice curve, and it will decrease over time. If we have a product, it will have a low concentration at the beginning, and it will increase. So this curve here is the reactants. This curve here is the products. Okay. Delta X is negative if it is a reactant because the reactants are consumed. And so the negative change of the concentration is a way to reflect the rate of the reactant being consumed. And then the change in concentration for a product is positive because it's being produced. The concentration is increasing over time. The concentration of reactants is decreasing over time. Okay, and we will do more kinetics next time. Thank you guys. I hope this was helpful. I enjoyed this. I love these two chapters, and this class is great. We're doing great. It's almost Halloween time. I got my costume and all that. My wife's going as a kind of a vampire, and I'm going as a vampire. And then my son's going to be the Invisible Man, and my daughter's going to be the werewolf. So we're all going as like the old school monsters, which is cool. All right, guys, have a great one. I'll see you Wednesday.